How's it going, ladies and gentlemen? Mr. Johnny here again with some 11.3 and 4 problems, properties of liquids and phase changes. Take a look at number 10. So which statements about viscosity are true? So remember, viscosity is resistance to flow. So let's think about this. Viscosity increases as temperature decreases. This is true, right? As things cool down and slow down, they're going to have stronger attractions to themselves, right? They're going to be held together more strongly. And colder things move slower, so you've got to move them out of the way, which would be more difficult if they're moving slow. So that's true. Viscosity increases as molecular weight increases is also true, because as the weight goes up, the attractive forces go up too, right? They're more polarizable, which means they're going to have stronger interactions. They're going to be held together more strongly, which is going to increase viscosity. It's going to be harder to move them apart. Viscosity increases as intermolecular forces increase. Again, that is true, right? So if we have two molecules that are held together by attractive forces, the more strongly they are held together, the more difficult it's going to be to move them. Right? All right, 11. The shape of a liquid meniscus is determined by blank. Remember, meniscus is, that curve of a liquid. If you're looking at a graduated cylinder, so it could be curved down, it could be curved up. Well, what's going on here? What's the difference? All right. Well, it has to do with the attractive forces between the molecules and the container. Well, how are they attracted to each other, as well as how the molecules are attracted to themselves. Right? We have a couple of forces going on. They're being held together to themselves, as well as being attracted to the container. So it is C. 11 will be C. It's the relative magnitudes of cohesive forces in the liquid and adhesive forces between the liquid and container. Remember, co is pretty much between the molecules, like cooperating, and add would be with something different. 12. The heat of sublimation can be approximated by adding together blank and blank. You got to remember that sublimation is when you have a solid that goes straight into the gas phase. That is sublimation. This is why they call it dry ice. It doesn't get wet. It doesn't go into the liquid phase. That never happens, so it stays dry. It doesn't melt. It goes straight into the gas. So, well, let's think about that. That's kind of like going from solid to liquid and then liquid to gas, but all in one step. So what values are associated with that? Well, the heat of fusion and the heat of vaporization. So if we take a look at number 12, the choice should be B. Heat of sublimation can be approximated by adding together heat of fusion and heat of vaporization. All right, 13. Phase changes B to C and D to E. All right, well, let's take a look at that. So we got B to C and D to E. We got heat added and we got temperature over there in degrees Celsius. They're not associated with the temperature increase because the heat energy is used up to do blank. Well, we're going solid here, and then solid to liquid, and then it's liquid. So this process right here is melting. And what's happening at that other flat part? Well, it's going liquid to gas. So we call that boiling, right? Or vaporization. So what's going on there? Well, you got to remember that solids are packed nice and close together in a nice orderly arrangement. And when it's melting, they break apart and they're free to move around. Right, so you're breaking that structure, that attractive force is going down. And same with boiling. Well, boiling, you got these liquids moving around, and then you go, you know what? I'm going to separate them completely so they have virtually no attraction for each other. So what's happening there? Well, A, you're increasing the distance between molecules. You're not making them move faster. You're just kind of spreading them out. 14. Based on the following information, which compound has the strongest intermolecular force? All right, well, let's think about this. We got heat of vaporization. So what are we trying to do with vaporization? Well, we need to take those liquids and we need to vaporize them and spread them all out and break those attractive forces. All right, so let's think about this. If we have the strongest attractive forces, those things are going to be held together more strongly. So would it need more or less energy to break them apart? Well, if they're stronger, you're going to need more energy. So if we're talking about the strongest attractive forces, we're probably going to look at the most energy. We're going to look for the highest thing here, which would be water, right? 40.8 is the greatest. 15. Substance with the largest heat of vaporization is blank. So again, you got to look at these and go, hey, I know something about these. They're all nonpolar. They're all diatomic molecules, you know, of the same element. So I know they're all nonpolar, which means that they're all going to have London dispersion forces. All right, well, let's think about this. We want the largest heat of vaporization, so that's going to be strongest attractive force. Well, when is London dispersion the strongest? So London dispersion forces go up as the mass goes up. As they get bigger, they become more polarizable, so they have stronger London dispersion forces. Which one of these things would that be? A. 16. Of the following, blank is the most volatile. All right, so you got to know what volatile is. A little embedded vocab question there. Volatile has to do with like how easily it goes into the gas phase. All right, if you think of gasoline, gasoline is pretty volatile. Filling up your car, you can smell it. That stuff is vaporizing pretty quickly without much problems. It's just like, oh, in the gas, it's volatile. So most volatile, well, why does gasoline go into the gas phase the most easily? Well, we want the weakest attractive forces, because the stronger the attractive force is, the harder it is to get it to become a gas. So the weaker it is, the easier it is to become a gas, the more volatile it is. So again, we have a bunch of examples here where they're all nonpolar molecules. So they're all London dispersion. So if we want the most volatile, we want the lightest. So which one of those things is the lightest? CH4 has the lightest one there, so it would have the weakest attractive forces and would therefore be the most volatile. All right, I like this one. A little math. Let's get our math caps on. To calculate the enthalpy change associated with conversion of 25 grams of ice at -4 to water vapor at that. And gives you a bunch of information. So if we remember what our phase change diagram is going to look like, well, all right, we always start with solid, heats up, it starts to melt. Now it's all liquid, it heats up, starts to boil, stays the same temperature, all of its gas, and then heats back up again. And it's saying we got this specific, amount of water. We got 25 grams at -4 Celsius. So we know we're starting as a solid. All right, so we're starting as a solid. So we got to go from -4. All right, first got to go from -4. Oops. As a solid, go from -4 to 0. And then we got to do solid to liquid, which would be the melting. And then we got to go liquid to the boiling point, right? We got to go from 0 to 100 degrees Celsius. And then once we're there, then we got to boil it. We got to go from liquid to gas. And because our final temperature is 106 degrees Celsius, so we know we're going to be in the gas phase. So now we got to also go, all right, well, now we got to go from 100 degrees Celsius to 106 degrees Celsius. So let's do some of that math. All right, so when we're staying in the same phase, like heating up a solid, that's when we're going to need to use a specific heat. So we got to use a specific heat of ice, being this. So we go, all right, 2.09 joules per gram Kelvin times the change in temperature, which would be 4 degrees, times the mass, which would be 25.0 grams. And what would you get? I'm going to write them down here. Solid to liquid, liquid to gas, and then as a gas. All right, so for the solid, you get 0.209 kilojoules. Now, be wary when you're doing this math. Where you're gonna mess up is some of the values are in joules, and some of the values are in kilojoules. And the question is asking for it in kilojoules. So I'm doing all my math and I'm converting my values to kilojoules, and I'm not showing that step because you guys should be able to go from joules to kilojoules without an explanation. All right. So then the next, solid to liquid. Well, that's melting, so we're going to have to use, you guys remember these formulas? Q equals mc delta T. That's for when there's a change in temperature, and the other one is Q equals mH, and then either F for fusion or V for vaporization, depends on which one. So for the solid to liquid, the melting, we're going to have to use the Q equals mHF. So I use M, which is still 25, times HF, which they tell me heat of fusion right here is 6.01 per mole. Oh man, so I gotta convert my grams to moles first. So I gotta divide that by 18. That gives me my moles, and then times that by 6.01, and I get 8.35 kilojoules. All right, so now once it's all liquid, so I added 0.209 kilojoules to get it from -4 to 0, right? So that was this section. And then solid to liquid, I had to add 8.35 kilojoules to melt it all. So now I'm here. I've made it this far. So now I got this liquid portion that I got to heat up to 100 degrees Celsius. So the math with that would be Q equals mc delta T. So M, 25.0 times C, specific heat of water, which they give me up here is 4.18 joules per gram degrees Kelvin, times the change in temperature, which will have to be 100 degrees Celsius. And I get 10.45 kilojoules. So now I made it all the way up to here. I had to add 10.45 kilojoules to get to this point. Now I got to boil it. So I'm going to have to use the heat of vaporization. So again, they give me kilojoules per mole, and I got grams. So I have to first convert grams into moles by dividing it by the formula mass. So now I got moles. I got to times that by the heat of vaporization, which is 40.67, and I get 56.5 kilojoules. And now I'm at this point. So now I'm at 100 degrees Celsius, and I got to heat up this gas until I get to 106 degrees Celsius. All right, so now I go, all right, well, again, it's going to be an MC delta T. So I got 25 grams times specific heat of steam, which would be 1.84 joules per gram degree Kelvin, times change in temperature, which would be 6 degrees Celsius, and I get 0.276 kilojoules. So now I just add all those up, all right? There's a bunch of steps, right? I had to go, all right, first heat up my solid. I had to add 0.209 kilojoules. Then I had to melt my solid. I had to add 8.35 kilojoules. Then I had to heat up my liquid. I had to add 10.45 kilojoules. Then I had to vaporize that, and I had to add 56.5 kilojoules, and then I had to heat up that steam, and I had to add 0.276 kilojoules. So I add all those up, and you get something like 75.8 kilojoules, which would be choice B, as in Bravo. All right, a lot of steps on that problem. I hope you were able to follow my sloppy work. If not, make fun of me in class or something, yell at me. But I will see you there.